to Mitchell. Welcome to this episode of AI Talks. And today we are very happy to have Mitchell as our speaker. So a brief background on Mitchell. He is currently a PhD student at the University of Washington, and he is interested in particularly three topics, which are large models, transfer learning, and robustness. And today, he will be talking about his research on how to fine-tune your large-scale models to make them more robust and accurate at the same time. So Mitchell, feel free to start whenever you're ready.
Yeah, thank you so much for having me here today. I'm very happy to be here virtually talking about our recent work. And yeah, so let's get started. So today we're going to be talking about how to fine-tune models in computer vision in a way that improves their robustness and also their accuracy. So to start, let's just revisit sort of what is the modern workflow in computer vision. So many high-performing models today in computer vision are produced by a two-step procedure. So you first take a neural network and you pre-train it on a lot of noisy data from the internet. So this is step one. Next, to adapt the model to a problem of interest, you fine-tune it, okay? And this is the second step, and this is actually the step that we're going to be focusing on today. And so the second step, fine-tuning, is becoming sort of increasingly important as better pre-trained models such as CLIP or GPT-3 or so forth are becoming available. So let's dive into sort of this second step. So why are we interested in fine-tuning? Well, with fine-tuning, you can often get better accuracy using less data. So to sort of look at one example of this, we can look at the commonly used ImageNet data set, where we can see that with only 10 examples per class, if you first pre-train and fine-tune, this is actually going to approach the accuracy of using the whole data set and training from scratch. So this is sort of just a quick motivation for why you should care about fine-tuning. I know probably a lot of you are already experts in fine-tuning, but just in case, yeah. So, but let's actually say like, okay, fine-tuning is good, but how is it actually typically done? So when we first started along this line of research, things have actually changed a lot since, but when we first started along this line of research, similar techniques were actually being used for both fine-tuning and training from scratch. So if we have sort of here a simple schematic for what training from scratch looks like, maybe we set some learning rate, and then we call some train function. If this is sort of a simple schematic here for training from scratch, then a lot of fine-tuning methods which perform really well are going to look very similar. The only difference is going to be that they're going to bump down learning rate, and they're going to make this call of loading a pre-trained model. So there's sort of a whole world now of parameter efficient fine-tuning methods and lots of interesting stuff there, but still many of sort of the highest performing methods, which are going to change all parameters, are going to look really similar schematically from training from scratch versus fine-tuning. Yeah, despite sort of differences which actually exist between these two regimes. So this motivates the question which our group and many other groups have been thinking about recently, which is, can we design better methods for fine-tuning? So the methods that we're going to be talking about today are going to leverage sort of a key difference between these two regimes, fine-tuning versus training from scratch. And that key difference is that fine-tuned models are often appearing to lie in a single low error region. So this is sort of what the techniques that we're going to be talking about today are techniques for sort of improving robustness and accuracy. This is what they're going to leverage. So this is kind of an informal claim. So what do we actually mean here? So first, let's look at sort of training from scratch, and let's sort of look at sort of how it looks from sort of an optimization landscape perspective. So say you start out with sort of a model here, theta 0. So this is your set of neural network parameters. and then you train it twice with two different random seeds to produce solutions, theta 1 and theta 2, which are also sort of just different sets of weights. So they live in sort of this, you can sort of think about a set of weights as just a d-dimensional vector. So they live in some d-dimensional space. They live in actually just this sort of landscape here. And what is this landscape? Well, points of low error here are shown in red, whereas points of high error are shown here in blue. So you can see that training has succeeded. It's found a point of low error both times that you ran your training procedure with two random seeds. However, it's found a different solution. So you ran it twice with two random seeds, and both times you sort of got this low error solution, but you found a different solution. And what do we really mean by different? We mean that if we just, these are vectors, so we can sort of just draw a straight line between them, we can interpolate them. And we see that if we do so, the neural network parameters, which lie right at the midpoint there, are not successful. This is sort of not performing well. This is an observation which is made sort of a lot of times. Recently, one paper is by Frankel, where they run this experiment and show that sort of linearly interpolating the weights of two models trained from scratch is going to encounter this high error barrier. So this is training from scratch, but fine tuning is going to look completely different. Fine tuning is going to actually look, so we repeat this experiment. Instead of training from scratch with two different seeds, we consider now fine tuning with two different random seeds. And it looks like this. So in contrast to training from scratch here, these models are appearing to lie in a single low error region, meaning that we can actually interpolate them, so just draw a line between these two weights that we got when we fine tuned with two random seeds. And the network there now at the middle is going to perform good. In fact, every network on this line is going to be a high performing neural network, a low error. It's lying in this red region. And this was an observation made by Neischaber in 2020. Accuracy remains high when linearly interpolating between the weights of two networks fine-tuned from a shared initialization. So please also feel free to interrupt me, just at any point, if people have questions. Okay, so this is sort of this key difference between fine-tuning and training from scratch. That fine-tuned models appear to lie in a single low error region. But what I just showed you was a cartoon. It's not real data. So we really want to now design an experiment which is going to sort of go from this schematic to real world data. So the experiment we're going to run to sort of convince you or try to convince you is to start out here let's again remember sort of this d-dimensional space. This is sort of the space of all neural network parameters, and we have our pre-trained models here represented by the star. Okay, and now we're going to fine tune it twice with two random seeds to produce both of these two blue solutions here. And so it's sort of, we can't visualize sort of this whole space because it's a d-dimensional space. It's all possible neural networks. It's just so large. But what we can visualize is all neural networks which lie on this plane. So just as 2 points define sort of a line, 3 points define a plane. And we can actually now take this plane, which is spanned by these 3 points, the pre-trained model, and these two fine-tuned solutions. This is just a two-dimensional plane, and we can actually just visualize the accuracy of all neural networks on this plane. So let's do that here for when fine-tuning. Clip the ITB32 model on ImageNet. And what we really see here is that this region is appearing roughly convex. Yeah, this is sort of what we mean by these fine-tuned models are appearing to lie in a single low error region. Okay, so while this observation was sort of was made by Neischaber et al. in the context of fine-tuned model pairs, what we're going to do today is sort of extend this. So we're going to say that we're going to show that interpolating models is actually not limited to identical pairs, which are fine-tuned on the same data. In contrast, what we're going to achieve high accuracy when interpolating many models which have observed different data and are potentially fine-tuned with different hyperparameters. Moreover, we're going to show that actually interpolating these weights can have ensemble-like effects. So it can achieve sort of the best of both models being interpolated. Yeah. So a final thing that's going to sort of we're going to do is actually we're going to leverage these properties to try to improve models, specifically their robustness and accuracy to achieve state-of-the-art on data sets such as ImageNet and out of distribution benchmarks from the WILDS data set. Okay, so that is the introduction. Please stop me yeah, at any point if you have questions. If not, let's get started by actually now diving into these individual papers. So first, we're going to talk about how to use this interpolation, model interpolation to actually improve robustness. Next, we're going to talk about how we're going to now generalize this to interpolate many different models and improve accuracy. Finally, we're going to talk about how to interpolate models which are fine-tuned on different data sets towards actually editing models. So let's jump into robustness. To get started, we're going to talk a little bit about how we evaluate models under natural distribution shift. Again, this is probably review for many people, but in case not, we'll go through it. So yeah, how do we evaluate models under natural distribution shift? So there's recently been interest beyond sort of evaluating a model on just the target distribution on which it is fine-tuned or trained. People are now caring about performance not just on this distribution, but on sort of related but different distributions, because we'd really like to eventually, yeah, we'd really like to sort of eventually be. Wait, sorry, am I sharing the right screen here? Can you see my speaker view or my slides?
Yes, we can see your slides.
Okay. No, you don't see my speaker view, right? Or is that?
No, we don't see your speaker view.
Cool.
So yeah, now we are seeing like your slide has two distributions on the left and right.
Okay, sweet. Just making sure. Okay, great. So yeah, so people are really interested in how our models performing on related but different distributions, which is sort of something that we need to be caring about as we're actually deploying models in the real world, and they're not going to look at like the real world is likely not going to be representative of this sort of data on which we train. So to zoom in on one particular distribution shift here that we're going to use today is ImageNet, which is sort of this target distribution which we fine tune on. Well, this consists of images that are uploaded by humans to the internet. There's sort of this ObjectNet distribution shift, which is going to consist of now centered objects, and these are going to be from various viewpoints. So here we see like lots of lemons where you might not typically see them. And to convince you that this is sort of a real problem for models, we can look at sort of a standard ImageNet trained ResNet, which is getting 76% on ImageNet. But on ObjectNet, its performance is going to drop by 40 percentage points. Well, this is sort of a problem for models, which are sort of standard ImageNet trained models. Progress towards this natural distribution shift was made recently by this CLIP model from OpenAI. And so while CLIP sort of matches the performance here of an ImageNet trained ResNet on ImageNet, getting also 76. Now, if we evaluate on ObjectNet, we see that performance is dropping now by only 4 versus 40 percentage points. So this is like a really nice improvement that OpenAI's CLIP model made on these natural distribution shift. And it's not just ObjectNet, it's going to be on sort of all of these other distribution shifts here. However, sort of like this 76 number that we're observing here for ImageNet, to put that in context, it's sort of like not, it's sort of where state of the art was around 6 or so years ago. So how things were looking sort of in 2016. So there's still room for improvement here. So we should try to actually like say, okay, great, clip is robust, but can we also make it accurate? So to improve clip, what we can do is sort of fine tune on data from the domain of interest. But we're going to run into an obstacle if we do this. And this obstacle is going to be that despite the accuracy improvements, which are going to be associated with this fine tuning is going to deteriorate clip's robustness if we just do so in sort of a naive way. So this raises the question, can we fine tune clip while maintaining robustness? So we're going to be looking at results today on a so-called effective robustness scatter plot, which looks like this, where we're going to look at accuracy on the target distribution, which is used for fine tuning. So ImageNet, for instance, on the x-axis, and then accuracy on distribution shift on the y-axis. So like ImageNet x-axis and then ObjectNet y-axis. And a useful reference point will be this sort of y equals x line here, because a model which lies, so a model here is a point on this plot, and a model which lies on this y equals x line has the same accuracy. Like accuracy is not affected by this distribution shift. It's got the same accuracy on both ImageNet and ObjectNet. And our target is not just to be on this line, but we want to be kind of in the upper right portion of this line. And we actually know this is a reasonable target, as for some of these distribution shifts, this is where humans actually lie. So when they do this experiment, for instance, on ImageNet versus ImageNet v2, this is where humans get. But if we look at sort of standard models which are trained on ImageNet, we see it's a different story. These models sort of lie below this diagonal, so they're doing better on D than they are relative to D prime. They have this performance drop, this under distribution shift. Whereas the zero-shot clip models are doing much better. They're sort of much closer to this diagonal. They're much more robust. So let's zoom in here on this region and look at what happens when we actually fine-tune clip, which is the following. We see that when we fine-tune clip, despite improved accuracy here on D, the robustness is decreasing. So yeah, so basically, we have these two different models at this point. We have clip, which is, so accuracy on D, but good accuracy on D prime. Whereas this fine-tuned clip model is going to get good accuracy now on D, but bad accuracy sort of out of distribution on D prime. And we really want sort of to get the best of both worlds. And how we're going to sort of propose to do that here today in the first part of this talk is just to sort of add these two models together, interpolate between these two models, take 1/2 the weights of this clip model plus 1/2 the weights of these fine-tuned models, and that will be the sort of model that we present. And yeah, that's sort of our method here is just going to be interpolating the weights of these two models. And we're going to call this sort of weight space ensembles for fine-tuning, because we're sort of taking these two models and we're ensembling these weights. So we can now go back to that plot and look at actually how this is performing. Here for various mixing coefficients alpha, which are going to be, so let's take sort of 1 minus alpha, the weights here, this purple model, the weights of this purple zero-shot clip model, plus alpha times the weights of the fine-tuned model. And now let's interpolate sort of with various mixing coefficients alpha and see where we end up. And we see that we trace out here this sort of pink curve. And what's really nice about this pink curve is that we can get a model here which has vertical movement, meaning that it improves accuracy under distribution shift without sort of sacrificing performance in distribution. This is just a schematic. So now let's look at sort of a real world data where we plot the average accuracy on the 5 distribution shifts that we looked at earlier. So like ObjectNet, ImageNet R, ImageNet V2, ImageNet Sketch, ImageNet A. On the y-axis and on the x-axis, we have ImageNet. And so we see here that the star is sort of the best, the purple star, the uppermost purple star is the best clip model. If we fine tune it, we produce this orange square. And now if we interpolate, we get this pink curve. And yeah, this is sort of corresponding to a potential 8.7 percentage point improvement out of distribution without loss in distribution. This is here for end-to-end fine-tuning, but similar, we observe similar things for when we train when you just train a linear probe here. So this is sort of the second curve here. And the linear probe case is somewhat interesting because then ensembling the weights and ensembling the outputs has no difference. Okay, so while we've so far looked at just sort of this image net distribution shifts, we actually observe in the paper sort of robustness improvements for a wide range of data sets. For example, the Wilds distribution shift from Stanford, where we see that we achieve 6.5 percentage points improvement on a set with a geographic distribution shift, satellite images with a geographic and temporal shift, standard sort of sci-fi distribution shifts, as well as perturbations from videos. We also observe sort of similar, qualitatively similar trends for different models such as basic L, JFT pre-trained models, as well as Align. And we also run a series of baselines, including sort of changing the optimization such that you're actually applying weight decay towards your starting point, your initial, so L2 regularization towards your initialization, or just in general, sort of changing the hyperparameters such as the learning rate and so forth. And we see that when you do so, you get sort of this different trend here, which is spanned by these. So the pink curve is the same as before. This is sort of the curve that we get by interpolating the fine-tuned pre-trained models. And now we see we can produce these other models, which are, having some robustness improvements, but they're still sort of lying below this pink curve. Similarly, we can look at early stopping. So how do things look if you just stop training early? And we see that this is this gray trajectory here. All these gray sort of trajectories are sort of like how accuracy looks as you're fine-tuning. So you can see that this is still lying sort of within this pink curve. Okay, so that's all for this sort of weights-based ensembles for fine-tuning, or WISE-FT method to improve the robustness of a fine-tuned model by interpolating this pre-trained and fine-tuned solution. But now we're going to talk about sort of generalizing this to actually interpolating the weights of multiple fine-tuned models. So now our focus is going to be on improving accuracy, and instead of just interpolating the pre-trained and fine-tuned models, we're going to interpolate a lot of model weights. So what is the conventional procedure for maximizing model accuracy? So let's say you had a deadline and you're just trying to get the best possible accuracy on some benchmark. What might you do is you might try sort of a bunch of different hyperparameters. So maybe you try some mix-up, maybe you try different learning rates and so forth. And this is in the context of fine-tuning. So you fine-tune a bunch of models with different hyperparameters. And then what you do is sort of you choose the model with the best accuracy on the held out validation set. And you say, okay, that's my model. I'm going to put it in the table. And you're going to usually discard the remainder of the models. These just simply didn't do as well, so you're not as interested. But this sort of this conventional procedure of sort of selecting the model with the best accuracy on the held out val set and discarding the remainder, this has a series of downsides. So for one, the model predictions are actually complementary, meaning that if we were to take a bunch of these models, run the data through all of them, and ensemble their outputs, we know that this would likely improve performance. So by throwing out these models, we're leaving some performance on the table. Albeit this ensembling comes at the cost of added cost during inference, because now you have to actually run it through all of these different models. Moreover, sort of when we took this best model and the held out val set and discarded the remainder, we might be leaving also performance on distribution shift on the table, because the best model on the target distribution may not actually be the best model under a distribution shift. So to sort of overcome some of these challenges, we're going to actually introduce model soups, which is an alternative to this conventional recipe of sort of taking one model and discarding the remainder. And what model soups is going to do is going to interpolate or average the weights of sort of many of these fine-tuned models together to produce a final solution. So that's the model soups, which is an alternative to sort of picking the best model and discarding the remainder. With model soups, instead, you're going to average together many of these weights. And so the two-dimensional slice of the error landscape that we were looking at before is going to provide sort of some intuition for why this might be something you want to do. So if we look here just at the middle column here, which is just ImageNet test error, we see, and so red is where you want to be. We see that the best performing solution is not any of your sort of individually fine-tuned models shown here as points, but it rather actually lies between fine-tuned solutions. And that's where we hope to get by averaging weights of multiple models. So while the most straightforward procedure is to just sort of take all your fine-tuned models and average them together, our best performing method is actually, we call it the greedy soup. So that's the uniform soup if you just take all the models and you just throw them all in a soup and interpolate all their weights. But the best performing procedure we present is this so-called greedy soup, which is a way to sort of like, let's say one of your fine-tuned models was bad, you don't want to add it in. The greedy soup is going to sort of take care of making it so you don't add a bad model in. So the procedure is straightforward. What you do is you first evaluate all models on the held out val set, and then you sort them by decreasing order of accuracy on this held out val set. Then what you do is add models sequentially to the soup, keeping a model in only if performance on a held out val set does not decrease. So we start here with our best performing model, and then let's say we add in this yellow guy, and we see that accuracy actually decreases, so we don't like that. So we go back to our original and proceed. Now we add in a pink and accuracy improves. So now we're going to keep that model in the soup and then we keep going. So that's the greedy soup procedure. Yeah, so let's look at sort of how this is going to perform. So here are results when fine-tuning CLIP VITAB32 model from sort of Radford et al. On ImageNet. And again, we're going to look at on the x-axis performance on ImageNet, on the y-axis performance on these distribution shifts. So we want to be sort of in the upper right here. And we're going to do a hyperparameter sweep over learning rate, mix up data log, iterations, weight decay rate, lots of stuff, just a random hyperparameter sweep. And that's going to produce these 72 green diamonds. So each of these green diamonds is just one of these models in this hyperparameter sweep. So we fine-tuned it and then we put it on the plot. And then what we're going to do is actually just average together all of these weights. We're going to just make a uniform soup. So put all these models, average together all their weights. And this produces now the blue circle. So this is okay, but it's underperforming one of the models on ImageNet. But when we now go to the greedy soup procedure and have a greedy averaging of these models, we're going to end up with here the purple star. So that's sort of what the results look like, which is good because we're able to produce sort of a better model here without any cost during inference, because since we're just averaging the weights, it's not like a traditional ensemble, meaning that we don't. It's not actually more costly at inference time because we only actually have sort of one model at the end of the day. So this is fine-tuning a CLIP VITAB32 model. But collaborators at Google ran this on sort of the more state-of-the-art settings that they have there, and we're able to get achieve a state-of-the-art on the ImageNet data set when fine-tuning a VITG model, and more recently a basic L model, which is a slight improvement on this. So next, we're going to look at sort of some motivations for like this approach. Like why does this perform well? And our sort of intuition is that this is the performance here is coming from the relation between this weight averaging procedure and output averaging. Our intuition is that things don't really move that much during fine tuning, and because of that, ensembling the weights is going to look a lot like ensembling the outputs. And this is some plots here which sort of show this. And in addition, there is analysis in the paper which is going to relate the performance similarity of these two quantities. So in these plots here, so two plots, one with ImageNet, this is the left plot, and and one with distribution shifts. This is the right plot. We put the accuracy of the model soup on the x-axis for two model soup for various model pairs. And on the y-axis, we have accuracy of the two model ensemble. And we see that things largely follow the diagonal here, meaning that the performance of the soup looks a lot like the performance of the ensemble. The notable exception here is these very light pink solutions, which are fine-tuned with a very high learning rate. If you fine-tune with a higher learning rate, now you might lose the basin and you might encounter a high error barrier when you try to interpolate. So this is a problem for model soups, but the good thing is that for the best performing models, which are sort of this medium purple models here, we still have this equivalence between averaging weights and averaging outputs. The other thing to note is that while things sort of follow the diagonal, it looks like that on ImageNet, things are sort of hovering a bit over the diagonal, meaning that ensembles are performing a little bit better than soups. Whereas under distribution shift, the reverse is true. So this is kind of a surprise, and we really don't know why this is happening. So why are soups outperforming ensembles out of distribution, while the reverse is true in distribution? Again, we're going to sort of not just look at ImageNet, we're going to look at more tasks. Again, these wild distribution shifts where model soups is also going to outperform previous approaches, as well as additional models such as align, shown here on the left, observing sort of qualitatively similar things to the clip results earlier, as well as basic L, which is achieving 90.98 on the ImageNet dataset. We also look at more domains, so text classification, where we see that we can also observe performance improvements, but it's not as sort of ubiquitous as the results in computer vision, because sometimes you actually don't see performance improvements from this procedure. So here's the leaderboards for these iWild cams, this data set with geographic distribution shift, as well as FMOW, which has the former has a geographic and temporal, whereas FMOW is just geographic distribution shift. Okay, so that's the end of model soups. And in the final part of this talk, we're going to talk about our recent patching paper, which is now going to interpolate the weights of models which are fine-tuned on different tasks. So far, we've only been sort of interpolating the weights of models which are fine-tuned on the same task, or the weights of a pre-trained and fine-tuned model. But there's sort of been like something that's somewhat restrictive about what we've been doing so far, which is that we've only evaluated on data sets which share classes with the fine-tuning task. So if we're fine-tuning on ImageNet, we're only evaluating on data sets which share classes with ImageNet. So like, that's how we're able to evaluate on like ImageNet R, ImageNet V2, ObjectNet, because those share classes, but we're not able to, for instance, fine-tune on ImageNet, but then evaluate on something like describable textures. So that's what we do now in this work, which is we ask this question, sort of, can we expand the set of tasks where pre-trained models perform well without reducing their performance on other tasks? So for instance, if we look at sort of a set of supported tasks, so these are tasks where a model like Clip is going to perform pretty well off the bat, not great, but not terrible. What we'd really like to do when we fine tune is not zoom in on one of these tasks in particular. Rather, what we'd actually like to do is sort of expand the set of tasks that this model is good at. And that's what we're going to do in this final paper, which we call patching, because we're going to refer to these as patching tasks. So we're going to sort of patch model performance on these tasks. So yeah, it's kind of funny because the Clip model, for instance, or especially the basic models, is performing really poorly on MNIST, which is surprising that it can perform well on ImageNet, but not MNIST. But really, we'd like to sort of like patch these holes in the model to make it perform well everywhere when we're doing these fine tuning. So we're gonna apply this sort of weight interpolation technique again here to do this. And that the results are going to be again shown on sort of scatter plots, where we're going to now put accuracy on the supported tasks on the x-axis and the accuracy on the patching tasks on the y-axis. And what we want to do is we want to fine tune now on these patching tasks without messing up accuracy on the supported tasks. So when we do that, we see the plot here, where we see that the zero-shot models are doing pretty well on the supported tasks, but not so good on the patching tasks. So these are the zero-shot models down here. On the other hand, the fine-tuned models are doing really well. So this is just fine-tuning now on these patching tasks. And these do really well now on the patching tasks, but performance is going to drop a lot on the supported tasks. But when we interpolate the weights, we see that we're able to produce a model which is now going to perform well on sort of all these tasks. So this is especially true for this large model, the VIT-L14, which it's worth noting is also has less of a performance drop on the supported tasks. Yeah. So we're going to look at various methods, or sort of the method that we use for doing that is sort of identical to WISE of T, where we first fine tune and then interpolate the weights of the pre-trained and fine-tuned models. However, now we're going to repeat this process multiple times for new tasks. And when fine-tuning, we're going to actually use a fixed zero-shot head. So we're not going to update the head when we fine-tune. Now when we go to a new task, we just swap in the new head. That's sort of the method here. And we can see that this method is actually an approach the performance of having multiple independent models per task. So like this sort of upper bound of just fine-tuning a different model on each task. And the paper contains sort of much more experiments. Like one interesting thing that we show is like, what's the accuracy? Like, can you have positive transfer across tasks where we fine tune on one task and then this helps on another task? So for instance, we show that with the satellite image data set. If you fine tune on Eurosat, this will make performance go up on another satellite image data set, RESISC 45. Okay, so that's the end of the main talk, but to highlight some sort of key related work in the space of sort of model averaging and interpolation. There's been lots of work showing that models remain in a low loss basin during the fine tuning. This is you know, the main inspiration for these approaches today. As well as other techniques which have looked at averaging the weights of models to improve accuracy. So like the fundamental works of Ismailov with stochastic weight averaging, and as well earlier works which use exponential moving averages. So the difference here is that these are averaging, the difference between these works and model soups is that these works are sort of averaging weights along a single optimization trajectory, whereas model soups is kind of now averaging weights across independent runs, which start with the same pre-training solution and may have different hyperparameters and so forth. Finally, we're inspired by work in sort of model ensembling, which shows that this hyperparameter diversity is going to help a lot with model ensembling by a collaborator, Rafa. To also highlight sort of the all the people that were involved in sort of this effort, a lot of phenomenal collaborators, many of which were equal contribution on many of these projects. Yes, is there a question? Okay, no. Okay, so, then, yeah.
So it's the end of slides?
Oh, just one more slide, sorry. Yeah.
Right, okay.
So to end with some sort of conclusions and future work. So far we've learned that sort of models can be merged together, achieving desirable properties of each model. While we've used this to improve models, in some ways, we've sort of only scratched the surface here. Like we sort of think that the future is going to consist of distributed and continuous collaborative model development, where like, you know, maybe University of Washington can fine tune for some task, and then other university can fine tune for another task, and then we can merge these models together, which is in line with sort of this these ideas of call and raffle and others of sort of model like open source development or developing models like open source software. So yeah, exciting times, and thanks for listening to